Alright, so vector representation. We've already done points on the Argand diagram where you've got x plus iy. We can basically represent them as vectors. So two vectors, p and q, on the Argand diagram are equal if both the modulus, which is like the magnitude of a vector, the magnitude of a vector, and the argument, in other words the direction, are equal. So the starting point, which we refer to as the tail, is irrelevant for a vector. It's always just where it starts from. It's taking it in some direction and moving it to somewhere else. Vectors will be studied as its own topic next term. Okay, so what do we mean by a vector? If I have, for example, y equals x squared, and I want to move that or translate it 2 units to the right, so I want to move that 2 units to the right and 1 unit up to about there. Do you guys know what the equation of that would be? X minus 2 squared plus 1. Yeah, exactly. X minus 2 squared plus 1. Now what we're really doing is we're taking this point here, we're moving it 2 places that way and 1 place up. Yeah? So that's the vector there. We're taking it from 0, 0 and moving it up. And like we could go and graph this whole thing, even if I took this point here and drew the same vector, same magnitude, same direction, and I could put a point in there. If I could do it the same with this one, same vector, same direction, same magnitude, and put it there. Same sort of thing here. Okay, same direction, same distance or magnitude, and put it there. So that the vector is just taking something and moving it somewhere else. Almost like a translation when we're doing, like year 7, moving points and stuff. Okay? At the start. So placing vectors head to tail. So P plus Q. Basically, I can take this vector Q, put it over here. It's the same vector. It's still got the same size. It's going in the same direction. And that gives us the vector P plus Q. And it's like we sort of form a parallelogram of vectors when we add 2 vectors together. If Z equals minus 3 plus 2i, and W is 2 plus 4i, draw Z plus W on the Argand diagram below. So Z is at minus 3 and 2. W is at 2 and 4. So I'll put W there, Z there. Drawing those in as vectors. And mathematically, you could go and work it out without the diagram. So minus 3 plus 2 is at minus 1, and that'll be 6. Whoops, that's not really a straight line. Z plus W. If we've got Z here plus W drawing the same line, same direction, same magnitude, okay, you can see that we're making that parallelogram of vectors. So Z plus W gives us that sort of diagonal of a parallelogram. Subtraction is similar to addition, but we go backwards to change the sign of the complex number being subtracted. So if we have P minus Q, so P here minus Q, P minus Q is almost like the same as doing, it is the same as doing P plus minus Q. So where would minus Q lie? If this is the vector Q, where would minus Q lie? Yeah, exactly, going straight back this way. So same distance, just in the opposite direction. So that would be minus q. So now it's like if I'm doing p plus minus q, if that's p here and that's minus q, adding them together, you can see that that's kind of creating that diagram of the diagonal of the parallelogram. So p minus q is that one in there. So it's the same direction. These two vectors are equal. It's the same direction and same magnitude. And just on that, we can kind of refer to this, if I make that capital Q, capital P, some notation that's useful in a few pages. We say that this vector here is going from Q to P, and we write that as QP with a line on top of it and a direction. So we're going from Q to P, can be written as P minus Q. Up here, Z1 plus Z2 starts from the tails of Z1 and Z2. So what's that? That's saying if we've got Z1, Z2, and we're adding them together, then we get that. And the typos in here, what should that be, do you think? A minus. This should be a minus in here. You can just fix that up. And so Z2 minus Z1. So we've got Z2, Z1 starts from the head of Z1 and goes to the head of Z2, like that. So when we're minusing, we get that other diagonal. When we're adding, we get the diagonal going that way. So Z is at 3 minus 2y. Z in there. W is at 2 and minus 5. So we've got Z, we've got W. Z minus W, what would that look like? Where would it start, where would it end? Yeah.
So start W.
Start W? Yep. Yep. So there. And you could do it using arithmetic. So if you go 3 minus 2, well that's 1. And minus 2 minus 5 will get us to 3. So you could see that this vector in there, can you see how that's parallel and equal to that one? They're going in the same direction and they have the same magnitude. Okay? Yes? So these ones, we start at the origin and we go to the point. Okay, and this notation up here, which we'll use in a little bit, see how it's QP? So we're starting at Q and we're going to P. And in terms of like whether you put the arrow up here or down here, because we're doing Z minus W, think of it as we're going backwards. We're going backwards from W because it's minus W, so we're going back here and then to Z because it's plus. Yeah. So scalar multiplication. Again, all of this stuff with vectors, you're actually going to start this next week in extension 1 as a topic, and then we'll do a topic next term on vectors as well. So Z is 1 plus 2y. Draw 3z and minus 2z on separate RGAM diagrams. So all it's saying is that if we have some sort of constant times Z1, stretch it by a factor of k. Yeah, yeah. So if we've got Z here, basically just timesing each thing by 3, we'll get the point, the vector at 3, 6. It's meant to look like a straight line. Kind of, maybe 3, 6 is more like there. That still doesn't look like a straight line, does it? Alright, and then, so all we're doing is just stretching it by a factor of 3. The other one we're stretching by a factor of 2, but it's going in the opposite direction. So that'll be at -2, -4. We've got 2 complex numbers and 0 on the argand diagram, and a third complex number, Z, forms a rhombus. Part 1, find Z in the form A plus IB, where A and B are real numbers. And I've got the answer there for you as well. Do you just, yeah, that's it. Just add them together. I'll do part 1 up here. So part 1, just plussing them, because that's going to give you that vector in there to Z. So 1 plus I root 3 plus root 3 plus I. And interior angle theta of the rhombus is marked on the diagram. Find the value of theta. What angles can we find out? And then might help us to work out some angles inside that rhombus. Yeah? Yeah. Yeah, so we can work out this one. Yeah? Yeah, all that stuff. What's that stuff called? What's it called when you find out the angle that, not mod arg, second part, the argument. So we're just finding the argument. We're just finding the argument of each of those complex numbers. What letters do you want to use to find? We've already got theta on there. Alpha. And? Beta. Alpha and beta? Okay, so 10 alpha. Thinking about where that is, 10 alpha in there. So that would be root 3, that would be 1. 10 alpha is 1 on root 3. Who knows what that is without the formula sheet? Pi on 6? I don't know, I have to draw the triangle to work it out. 1, 2, square root 3, 60, 30. Pi on 6, very good, thank you. And then 10 beta. 10 beta is just the other way around. So we'll have root 3. So beta would be pi on 3. Well, with that information, we could. With that information, we can work out that part.
Is that equal to that? Yeah, that's equal to like.
So that's beta minus alpha.
So it's 30 degrees.
You can subtract them. So subtract them to get that internal angle, that little small one in there. So beta minus alpha. So pi on 3 minus pi on 6. Pi on 3 minus pi on 6 is pi on 6. But we're not trying not to overcomplicate it. Let's just think back. Like now I know what this angle is. If I draw that diagram separately, thinking back to year 7, if this is a rhombus, and I'm saying that this angle here is 30 degrees, can you work out what the other ones would be if it's a rhombus? Yeah, so this will be 30 and 30, and yeah, that would be 150. Would be 150 degrees because the rhombus, yeah, you've got that parallelogram happening, and angle sum of a quadrilateral is 360 also. Now they've written it as 5 pi on 6 in the answers, so it is 5 pi on 6. So if we have Z1 and Z2, so if I have a point P, Z1, and a point R, same for Z2. If I add them together, we'll get the point Q, which is kind of maybe parallel. So if I kind of move R, Z2, over to here, that'll get me the point Q, which is Z1 plus Z2. So just making that parallelogram. And using some of the vector notation, Z1 is the vector from O to P. Z2 is the vector from O to R. And the modulus of Z1 is equal to the distance OP. And likewise the modulus of Z2. So this is just some notation to kind of think about and start using. So this distance in here, Z1 plus Z2, mod Z1 plus Z2 is equal to OQ. And likewise, if we look at the distance Z2 and Z1, so Z1 minus Z2, that's equal to RP. So thinking about we're going back from Z2 to Z1, we're going from RP. Just this is the sort of notation that I'll be using to have a look at this next part. The first inequality, this one up here, this first one here is basically saying that the longest side in a triangle has to be less than these two added together. Why? If this one is bigger than these two, then it's not a triangle. If it's the same, what happens if this distance in here is equal to that plus that? They're the same, they lie on a straight line? Yeah. Okay? So that's kind of what that's saying, and I'll just write that down in words. And the second one is saying that this distance in here, it's saying that going backwards this way must always be greater than that one in there. So the second inequality means the side of a triangle is more than the difference of the other two sides. So all it's doing is just using the previous inequality from the top, which is Z1 plus Z2 must be less than or equal to Z1 plus Z2 separately. What's the modulus of Z1? You should be able to see that straight away. 5. So modulus of Z1 is 5. Modulus of Z2 is 13, so So the greatest value of Z1 plus Z2 is just 18. If it is at its greatest value, find the value of Z2 in Cartesian form. Okay, so if we've got 3 and 4i, that's here somewhere, call that Z1. If it is at its greatest value, what does that mean if it's at that kind of limit with Z1 and Z2? Kind of talked about it before with the triangle. What happens if they are at that greatest point and they are equal? It's a line, exactly, yeah. So if it is at the greatest value, then Z2 is just going to be a continuation of that and over there somewhere. So this is obtained when Z2 is equal to some constant times Z1 for some positive value of K. But we already know that the modulus of Z2 is equal to 13.
Miss, what's K?
Just a constant.
Where's the constant?
I made it up. Okay, well, I have written here obtained, for some positive, I didn't make it up. If you look on the previous page, look back on page 24 where we did scalar multiplication, page 24. So we're doing KZ1 where K is an element of the real numbers, we're stretching it by a factor of K. Yeah?
K is like,
For some positive real K. It's a constant, like C, not yeah. Okay, so the modulus of Z2 is 13. Z2 is also equal to K times Z1, but the modulus of Z1 is 5. So 13, if you think about the modulus of both of these, 13 must be equal to K times 5, because the modulus of Z1 is 5. So K is equal to 13 over 5, 3 plus 4i. And then you can just tidy that up by writing it as 39 over 5 plus 52 I on 5. By I, let Z equals R, so Z equals R e to the I theta, that's just our exponential form. Then I times Z is equal to R e to the I theta, which is just Z, times e to the I theta on 2, and then we can add them together. So multiplying by I corresponds to a rotation through a right angle in the anti-clockwise direction. Now, how does that work if we are multiplying by I? Thinking about if Z equals R cos theta plus I sine theta, what value of theta will just get me I in there? 90, pi on 2, yeah? So if we have R times cos pi on 2 plus I sine pi on 2, that'll become 0, that'll become 1, and we'll get just I in there, which is why in that exponential form here, that's just R cis pi on 2. So writing it in that exponential form, not R, sorry, we've already got R there. So if we want to rotate a complex number 90 degrees anti-clockwise, it's the same as multiplying by I. And we can verify that down here. So if Z equals 3 plus 2I, verify that IZ is Z rotated 90 degrees about the origin. So IZ is I times 3 plus 2I. 3I, that'll become I squared when you multiply, so minus 2. Where does the first one, 3 plus 2I, it's here, Z, IZ is at minus 2 and 3. We'll get that right angle in there. You could go and, I guess, find the argument of that one, and then find the argument of IZ, and then subtract. Now, it's a little bit tricky because you're going to get 2 on 3, and not nice surds to work with. And then when you subtract, you would get that it's 90 degrees. So if I draw a diagram, OP is at 3 plus 4I, so we'll say maybe here somewhere. And it's isosceles right angled, so we know that there has to be a right angle in there somewhere. How many, where is the right angle going to be? So the easiest one, which is the first case, is going to be when the right angle is here. That's a right angle, okay? Just believe me. Alright? So that's scenario 1. Scenario 2. Scenario 2, there's a right angle up here. It may or may not be in line with that. So we've got OP. Here we've got the right angle at O. Here we've got the right angle at P. Are there any more? Right angle at Q. Okay. Doesn't need to be to scale. Alright, so O to P and O to Q. And we're trying to find what this complex number would be. So what's happened to this line here to get to this line here, OQ? What's happened to it? It got rotated 90 degrees in the anti-clockwise direction. So times by I. Very good. So scenario 1, if the right angle is at O, the complex number Q would just be I times P. So I times 3 plus 4I, which will become minus 4 plus 3I. Because I squareds will become minus 1. And that's the easiest one out of these three to understand, I think. Now, this next one, the line that's been rotated to get to Q is the if you think of it as a vector, is PO. So it's like we're saying we're taking this number here and we're rotating it around to get to QP. So in other words, P to O has been rotated minus 90 though, not just 90, because we are going in the clockwise direction. So it's rotated minus 90 about the point P, not the origin, and that becomes that line there, PQ. So from P to Q. So P to O, now that's when I said, remember this one I wrote up here before? This is important. P to O is just going to be O minus P, other way around. So thinking back to this notation that we said before, it becomes O minus P, but we're multiplying it by not just I this time. We're still multiplying by I, but we're actually multiplying by minus I because we are going in the clockwise direction. PQ, which is like Q minus P. So just again to reiterate, we've moved this line, this vector here, PO, is rotating around and becoming this vector here, PQ, so they must be equal. Multiplying this through, we get IP equal to Q minus P. Now we're trying to find what Q is. So if we just rearrange and replace with everything else. Now IP we already worked out down here. So Q will be equal to IP plus P. So minus 4 plus 3I plus whatever P was, 3 plus 4I. So I'll write it down there. 4 plus 3 is minus 4, sorry. Plus 3 is minus 1 plus 7I.
Yes, where did the negative I
Oh, that's 0.
oh.
That's 0. That's 0 for the origin.
Minus P.
No, because you rearrange. So Q, we want Q. Q is equal to IP plus P. Maybe I skipped a step. I should have written underneath this Q equals IP plus P. I skipped a step. So I was running out of room. So if we have from Q to O, so the vector QO, rotated 90 degrees. Now we're going 90 degrees in the anti-clockwise direction to become QP. So Q to O is O minus Q. Sorry, I should say 0, not O. It's 0 minus Q. We're rotating 90 degrees, so what are we multiplying that vector by? I. Becomes Q to P, which is P minus Q. Rearranging that for Q, so we'll get minus IQ equals P minus Q. Moving Q over and factorising, 1 minus I equal to P. So then Q is equal to P, which is 3 plus 4I, all over 1 minus I. And then what? Times 1 plus 4I over, 1 plus I over 1 plus I. And that's it for today. And then down the bottom it does just tell you again that if we rotated in these ones by 90, so it was multiplying by cis pi on 2, but you can actually rotate anything by any angle by multiplying by cis of the angle, which is down the bottom there.